All right. Section 3.1, vector spaces. Part of the purpose, well, one of the purposes of in this course is that we can see we can study vector spaces. Vector spaces is a very abstract concept in mathematics, but first we will try to understand this first in the simplest way. What is the motivation? Maybe you know that a vector we understand as a vector something that has a magnitude and direction. Magnitude and direction. And that interpretation is okay. So we can say that the vector depends on two things, right? I mean, it has like two numbers associated to the vector. Or well, maybe from physics as well, you can understand vectors as some kind of segment of line with an arrow. For example, this. This can be interpreted also as a vector. And here we are in the Cartesian plane, x-axis, y-axis. But notice, if we try to represent a vector in this way on the Cartesian plane, then necessarily in the endpoint, if we consider the initial point, the origin, then it has an endpoint. Let's say that the endpoint is this one. So we can represent the vector only by the endpoint, of course, if we assume that always the initial point is the origin. I mean, this is the point 0, 0, origin. But these two coordinates, I mean, this point has two coordinates and they determine the vector. We can say that this has coordinates A, B. So we can say that in this way, we can say that the vector is only these 2 points A, B. So I would say that I'm going to call this by B with this symbol. I'm going to be using this symbol to represent like the letters involved. Yeah, I know it's hard to write or to express here the letters involved, but instead of doing that, I'm going to put this symbol in the top for each letter when I try to represent a vector. So in this case, if I'm saying this is a vector, then I can say that the vector has only two components, A and B, you see? And of course, the order is only an ordered pair. of numbers. So if we consider all the pairs in this way, then we can say that if we consider all the vectors in the form AB, then we have R2. That usually this is called the Cartesian plane. I mean, this is all the points that we can have on the Cartesian plane. I mean, including the 4 quadrants. This is when we have a vector, of course, with 2 components. Yeah. Of course, what about if I want to represent a vector with more than 2 components? Well, in this case, we can also have the vector, for example, x with 3 components, a, b, and c, or in the same way, x with a, b, and c. In this case, if we try to interpret this geometrically, then the vector can be represented in the 3-dimensional space. In this case, I can say the vector, this is the initial point in the 3 dimensions, and I can say this is the vector with the elements A, B, C. So again, I have something like a segmental line that has that for sure is going to have a magnitude and a direction. But the main point, and the point that I want you to get that a vector is completely determined by 3 numbers with the corresponding order, of course. So in this case, we can say that all the elements, all the vectors in the form ABC, they form R3, that is the 3-dimensional space. Yeah, so this is one way to represent vectors with only 2 components or 3 components, but they have an order. All right. But now, how can we define this in a more general way? In a more general way, notice we have defined a vector as 2 numbers with order and 3 numbers with order AB or ABC. But why to stop only at 2 or 3? I mean, why not to put ABCD or ABCDE more than 3 numbers or more than 4 numbers? So of course we can do that, and that's going to be a vector as well. First, remember here we're going to be using many things of sets. remember that set can be understood as what? A collection of items or things. Here in this class, we're going to be working a lot with sets. So it's important that you remember, some properties. When I need some properties, I will let you know. But essentially, a set is a collection of items, collection of things, collection of anything. That is a set. All right. Now, a collection of items or things. Now, we can define not only as we did it here, that we notice I have here R3 and R2. How can we define Rn for any n that is a natural number? Well, in this case, we have Rn is the set of all the vectors or elements such that they have the form x1, x2, and so on up to xn, where x1, x2, and so on are real numbers. So essentially a vector in Rn, and of course n, is a natural number. So for example, in this way, I can say that the vector 1, 2 is in R2. The vector 0, -1, 3 over 2 is in R3. The vector 1, 0, pi, square root of 2 is in R4. The vector 0, 0, 0, 0, 0, 0 is in R6, and so on. All of these are going to be vectors. Yeah. So vectors is like a sequence of numbers that, of course, they have a well-defined order. So we will refer to the elements of Rn, that is this one, for any n, where n is a natural number, from now on as vectors. Vectors. The vectors can be represented like this: x1, x2, xn, or as one row: x1, x2, and so on. All right. Now, Rn, as defined before, is an example of something called a vector space. In general, a vector space is a set with two operations satisfying certain properties. So by now, I won't talk about vector spaces in general, but you need to know that Rn, this is a vector space, and its elements are vectors. So based on this, we are going to see two operations. Two operations there are two operations defined in Rn. They are sum and scalar multiplication. The sum is defined like this. If we have x plus y, where x is only x1, x2, and so on, up to xn, plus y, and y is y1, y2, and so on, up to yn. The sum is only add element by element. So like matrices, right? Yeah, by the way, yeah. I have talked about matrices, operations with matrices. So yeah, vector is only a matrix with one row or one column. Yeah, that is a vector essentially. So you add this x1 plus y1, x2 plus y2, and so on. xn plus yn. The other operation, the scalar multiplication. Scalar multiplication. This is if C is a real number, then you multiply C times a vector, and this only multiply each component by C. And there you have. So we have Rn, that is that we said that its elements are vectors, and this is a vector space. It has two main operations defined on it, that they are sum and scalar multiplication. And yes, a vector can be thought as only one row matrix or one column matrix. But next, these operations, they satisfy certain properties. First, these are called closure properties. Number one, if you add two vectors, then the sum is in Rn. Number two, if you multiply a real number times a vector, then this multiplication is in Rn. What is the meaning for this? It means that one property that if you sum two vectors, that result, that vector is going to stay in the same space or the same set, Rn. If you multiply a constant times a vector, or you do the scalar multiplication, that multiplication is going to be in Rn as well. So that is the meaning for these properties. I mean, the operations, sum and scalar multiplication, always they produce results or vectors in Rn. Now, addition properties. Addition properties. Number one, if you add x plus y, this is the same as y plus x. Yeah, I think it makes sense, right? But yeah, this is a property that we assume as truth. Number two, if you add x plus y plus c, it's the same as you want to do first x plus y and then plus c. If you want to add first the vectors y and c, and then you want to add this result to x, it's the same as if you want to add first x plus y and then c. We're assuming that this is true. Number three, there is a vector that is going to be called the zero vector, such that for any vector in the vector space, we have that x plus the zero vector is the same as 0 plus x. So this property means that always in Rn, we have a vector satisfying this property, that when you add this vector to any other vector, the result is the same vector. I mean, we can say that this zero vector does nothing when we apply this operation to any other vector. Number four, for each vector x, there is negative x, such that when you add these two, you have the zero vector. I mean, this means that for any vector, we can always find its inverse with respect to addition, such that when we perform the addition, we end up with the zero vector. Like this is like in the real numbers, right? Scalar multiplication properties. Number one, if you multiply A times B times the vector X, it's the same as AB and then times the vector X. A and B are real numbers. Number two, A times the sum of two vectors. You can apply something like a distribution property, that is A times X plus Y plus A times Y. And again, A is a real number. Property number three, A plus B times X is the same as A times X plus B times X. And of course, A and B are not vectors, they are real numbers. And number four, if you want to multiply the real number 1 times any vector, you get the same vector. So these are the with these properties, this 1, 2, 1, 2, 3, 4, with these 10 properties, Rn forms a vector space. So essentially, a vector space is some kind of set with, in general, with two operations, sum and scalar multiplication, satisfying these properties. The example we have so far is only Rn. Remember that Rn in this case, in our context, is only a sequence of n real numbers by now. By now, that is. And it satisfies all of these properties. Now, some of the exercises you're going to see in the assignments, they will require that you will have to follow or try to indicate a proof, a mathematical proof. Well, I know that maybe this is going to be new for most of you. Anyway, don't worry about it. I think it's going to be simple, but I will try to explain how you should do that. Example: prove that if in Rn we have x plus c equal to y plus c, then x is equal to y. So we have to prove this. And how we must prove it? Let's say that this is like a game. We start with Rn, and we know that in Rn, we have two operations. And the operations, they satisfy this property. So everything or anything that you can prove based on these 10 properties, you can consider that as a true result. Okay, so one true result in any vector space in Rn, if you have x plus c equal to y plus c, then you can conclude that x equal to y, because notice we have the same c here. But of course, this must be proved by following some of these 10 properties, and it's not very complicated. Notice, proof. We start with x plus c equal to y plus c. And pay attention to what you want to prove. We want to prove that x equal to y. So if we start with this, so maybe we need to find a way to cancel the c. And remember, these are not real numbers. These are vectors. We're working with Rn. So what property can I use out of the 10 properties that I have to cancel the c? Notice there is the property number 4 for addition. It said that any vector has other vectors such that when I add it, I have the zero vector. So I would say here, from property 4, of addition, I have x plus c. I can add at both sides the inverse for c. So will be c is equal to y plus c plus c. You see? How do I know this element? How do I know that I can do this? Because of this property. The property number 4 says that always for any vector, there is an element, it's reciprocal respect to addition, or its inverse respect to addition. Any vector has that. C is a vector, so it has that. Now, what do we know? C plus negative c is what? This implies that this is equal to c to the zero vector. So I have this, y plus the zero vector at both sides. But when you add the zero vector to any vector by the property number 3 of addition, this one, we have the same vector. So this means that this becomes x equal to y. You see? This is because property of zero vector. And there you have. We have proved that if x plus c is equal to y plus c, I mean, we are adding at both sides of the equation the same vector, then we can cancel that vector to end up with x plus y. Is that okay? All right. Please, there are some exercises in the assignment where you will have to kind of indicate or try to follow the proof, right? You will have to choose the right sentences. So try to do it. Anyway, if you have any question, remember you can let me know. See you later.